So, welcome to this lecture number 7 of solar photovoltaics principles, technologies and materials. So, let us just recap the past few lectures. In the past few lectures, we talked about solar radiation. Basically, what are the components of solar radiation? How do we quantify it? And then we looked at for quantification we require geometrical relation. We require first of all the energy that reaches the outside layer of the earth. So, we can say solar, we define solar constant, basically leading to extraterrestrial radiation falling on the surface of earth, and then we defined air mass, which means whatever energy is coming on the outside, when it reaches earth surface, how much absorption does it go, and based on the absorption which is coming at, because sun ray does not always come at zenith, it always because the movement of sun, the radiation undergoes different lengths of absorption in the atmosphere. As a result, you need to define air mass. So, average air mass is 1.5 g. This is what is average intensity when we characterize the solar cell for the averaging for the whole day. And then we looked at the geometrical relationships. So, because solar panels are not horizontal on the surface, they are always at certain angle and hence they make certain angle to the sun beam, and in order to calculate those angles you need to know geometrical relations. So, we looked at things like zenith angle, solar altitude angle, solar azimuthal angle and so on and so forth, and then we also defined various time corrections, and time corrections together with geometrical relations give you rather accurate estimate of the angle at which angle and the time at which the radiation is coming and falling on the surface. And then we looked at various model for measuring solar radiation. So, all of this makes a complete sort of study of how do you measure the solar radiation falling on a surface at a given location at a given time of the year. So, all of this is required to, so it is not in very great detail because it is just 5 half-an-hour lecture worth material. However, if you wanted to go into details, I have given you references such as principles of such as solar energy by Sukhatme and Nayak, principle of solar energy engineering by Caligrove. These are good books which go into details of solar radiation measurement. So, now we will get into learning the fundamentals of semiconductors, which are basically on the core of photovoltaics. So, we will look at some basic principles of semiconductors. Now, the semiconductor, as the name itself suggests, is semiconductor. It is not a completely conducting material. Based on the electrical properties of materials are defined in 3 categories. So, the first type of materials is called as conductors, or you can say metals, which show high electronic conductivity, electrical conductivity, and then we have semiconductor, and then we have insulator. Okay. And the property which defines these distinction is basically, you can say, defined on the basis of electrical conductivity, which is written as sigma is equal to n E square tau divided by m, okay, where n is the carrier concentration, E is the electronic mass or carrier mass, tau is the relaxation time, and then m is the mass of the carrier. You can also write this equation as n E mu, where mu is the carrier, sorry, just spell it right, carrier mobility. Okay, so you can see that mu will be equal to E tau divided by m. So this equation gives you the conductivity, which is inverse of resistivity rho. So essentially this is electronic conductivity, and based on the value of this conductivity we define a material as a semiconductor or as an insulator or as a metal. So let me so the distinction between these three is it takes a value of about let us say, let me give you certain values. So semiconductors would be, so metals would be the ones, they will have large sigma, or you can say small rho. So typically a metal would have conductivity. So metals conductivity is of the order of you can say ohm meter inverse. So something like something like copper would have a conductivity of, I don't know, 10 to the power 6 to 10 to the power 8 ohm meter inverse, something like that, okay, within the range 10 to the minus 8, 10 to the power 8 inverse. So you can say resistivity would be 10 to the power minus 8 inverse ohm meter. Semiconductor on the other hand, will have electrical conductivity of somewhere between so they will have medium, or you can say smallish sigma. So this would vary between anywhere from 10 to the power minus 1 to 10 to the power plus 2 or 3 ohm meter inverse. So silicon would have a value of about so for example silicon will have a value of about 10 to the power 10 ohm meter 1 to 10 ohm meter inverse. If you look at insulator will have very small conductivity. So essentially you are looking at conductivity of the order of 10 to the minus 8 or lower. So in this category you will have most of the compound materials, oxides, nitride, carbides. Many oxides are very insulating, so they will all be in this category. Now we will come back to this later on, but first we would like to see what is that which tells you the difference between a metal, semiconductor and insulator, and this is basically on the basis of energy band diagram. So the energy band diagrams, because I mean we know from the fundamentals of quantum mechanics that energy is quantized, and energy of a electron is can be written as, so energy of an electron is written as E is equal to h cross square k square divided by 2m, where h cross is equal to h divided by 2 pi, where h is Planck's constant. Okay. And k here is called as wave vector. So k is essentially, if you write k is nothing but 2 pi divided by lambda. So it is inversely proportional to the wavelength. So lambda's unit says, if lambda's units are in length, then k's unit are in reciprocal of length, which means if lambda represents what we call as real space, k represents what we call as reciprocal space. Okay, and m is nothing but mass of electron here. Now in terms of lattice also we define what we call as lattice vector, which could be x, a, b, c. Okay. but lattice also has a reciprocal lattice vector which is A star, B star and C star, and the magnitude of this reciprocal lattice vector is inversely proportional to the magnitude of real lattice vector. So, basically what you do is that you take a lattice point and corresponding to that lattice point you have a reciprocal lattice points, and the reciprocal lattice and the distance from the origin to that reciprocal lattice point is nothing but inversely proportional to the real lattice vector. Okay. So, basically we say that for a given HKL, if you have D star HKL, which is the reciprocal lattice vector length, that is equal to, so this is reciprocal and this is real. Okay. This is the difference that you have. Now, what happens is that when you plot this E versus K for a single electron, it is like this. So, we have this is E and this is what is K. Okay. So, it goes from, so K can, it is a wave vector, it can go to minus K also, it can take both the values plus and minus K, it makes a parabolic shape. Okay. Now, there are various approximations of electron being confined, electron being present in a material. So, electron can be loosely bound, electron can be very strongly bound. So, that defines the value of potential that is present in the lattice. So, we know that if you have a lattice like this, okay. So, if you just take a one dimensional model of lattice, then you can see that if you plot the periodic potential, the potential in the lattice is basically the surface potential would be something like this. How do I plot it? If I take this as the, so this is nothing but you can say the potential, I do not know, potential can be written as V and this can be taken as distance x, and here the potential varies as something like this. So, this is, you can say it is nothing but periodic potential. So, you are going to have periodic potential in a periodic lattice. Okay. And if you do not have a periodic lattice, you will have a aperiodic potential, which means potential will not also have a periodicity. Now, based on, now when you, and this is the energy versus wave vector for single electron. In a material you do not have single electron, you have multiple electrons, and you have these, all the lattice sites will have this kind of periodic potential. So, based on the interaction of electron with the lattice, when the electron interacts with the lattice, then when you plot Ek for a given lattice, so when you can say electron and lattice when you take together. So, this has whole theory behind it, Kronig-Penney model and so on and so forth. We do not have time to discuss all that, but when an electron is present in a lattice, it undergoes interaction with the lattice, and based on that you can plot the energy of electron as a function of, now this wave vector of electron, that is a small k, and reciprocal lattice vector capital K, they are related to each other. Okay. Because both of them are in reciprocal space, you can relate them to each other. So, essentially what you do is that you plot the energy of electron in the reciprocal space. When you plot the reciprocal, when you plot this energy of electron in reciprocal space, you will have and these vary from one plane of reciprocal lattice or one boundary of reciprocal lattice from another boundary of reciprocal lattice and so on and so forth. So, they represent variety of these kind of lines. Okay. So, you can have structures, you can have this kind of curves going all over the place and so on and so forth. So, I am not drawing in particular any particular diagram, but this is how lines you will observe. Now these are the lines which are energy versus, let us say, K. Okay. Now as long as these lines are connected to each other and they are continuous, so that electron will, so suppose you have electron here, when it moves, it always finds a continuity in the energy space. There is no discontinuity in the energy space. So you can see that although there is a discontinuity here, but you find electron finds a continuity here. Similarly, if it travels from this energy space, it always finds a continuity here. So as long as electron is able to find a continuity in the energy space, it will always find an energy state in which it can move into. However, if there are systems for which you do not have continuity, if there are systems for which you have situations like, so if you plot E versus K, and if you plot, let us say, you may have states in this fashion, let us say, very simple diagram I will draw. So you may have states like, okay, if you have states like these, then, so this is, let us say, K1, this is, let us say, K2. So if you look at, without getting into this, if you look at this state, what you have here is you have a discontinuity at these K values, and if this discontinuity is if this cannot be overcome by electron energy in a given system, then this is called sort of an energy gap. So the systems where you have these discontinuities in the energy states in the K space, which are large enough so that they cannot be crossed over by electrons, they are generally semiconducting or insulating in nature. They will have forwarding energy gap, whereas the systems in which energy states are continuous, they are generally called as metal. If you look at the band structure, so band structure is far more complicated than what I have drawn here, but if you look at the band structure of a metal, let us say, so let us say this is for a given metal E. So if I plot, so this is the first boundary of K space, this is the first line. Let me just remove these. This is the first boundary. Okay. Now at this boundary, so let us say I have few of these regions. Okay. So I can keep plotting. So in this case, it goes from something like that, and then let us say you have this energy state, then you have this energy state continues like this energy state continues like that, continues like this. Now you can see that although you can see that there are certain discontinuities in the energy space here, but there are certain energy states which are continuous across the energy spectrum. You have certain gaps here, you have a gap here, you have a gap here, but at the same time you always find a continuity. So this energy state is continuous, this energy state is continuous, and this energy state is continuous, which provides a path between these energy states. So there is a connectivity in the energy states. There is no single gap which runs through the K space. So this is sort of a energy band for a metal. Okay. So this is K without a gap which runs through the K space. On the other hand, if you look at semiconductor, what will happen in a semiconductor is something like this, and the same will be true for energy for the insulator also. So for a semiconductor, you will have this E as a function of K, and this E could be something like this. Okay. we have and so on and so forth. So, now here what you see is that there is one region in which energy states are continuous, there is another region in which energy states are connected to each other, but there is one region where there is no energy state at all. So, you can see that if I just connect this region, so within this region I have no energy state. If you compare this with previous figure, in the previous figure you had no state. So, if you, for example, if you say this is the gap, but somewhere you had energy state, this is the energy state that is present. So, there is not a continuous region in the K space when you do not have energy state, you always have some energy state present at certain in the K space, but there is a diagram now here where you do not have any energy state present anywhere. Now, this is what is, so this is EK diagram, energy versus wave vector diagram, and we see that there is a gap, and this gap is called as forbidden energy gap or the band gap. So, the lines which the energy lines, energy states which lie below this energy gap, they are called as, we depict them as valence band, and the lines which lie above this, they are called as, the energy states which lie above this, they are called as conduction band. And depending upon the magnitude of this gap, a material is semiconducting or insulating. So, if this energy gap is up to roughly 2.5 eV, so if Eg is then 2.5 eV, then we call it semiconductor, and if Eg is greater than 2.5 eV, we call it insulator, and metals do not have a band gap. Okay. So, metals do not have a band gap. So, based on this configuration of EK diagram, we define, so this is the distinction between a metal and a semiconductor. In a metal, the energy states are continuous all across the spectra. So, you can have variety of energy states all across the spectra, they crisscross in such a manner so that you do not have a continuous gap across the K space, whereas in case of semiconductors you have a gap in the K space, a well defined gap in the K space between the maxima and minima. Okay. Now, depending upon the position of this maxima and minima, so now depending upon the position of this maxima and minima, I am not going to draw all the states. So, let us say we have a, this is the valence band, conduction band, energy band, this is the valence band structure. Okay. So, valence band is something, this is valence band, this is conduction band, and so on and so forth. So, this is E, this is K. So, K is a reciprocal space. If the minima of conduction band and the maxima of valence band do not coincide in the K space, so you can see they have a gap, and the gap is always with respect to maxima and minima. Okay. If the K, you can say conduction band minima and K with respect to valence band maxima, they do not coincide, if they are different, then this kind of semiconductor is called as indirect band gap semiconductor. However, if you have a situation in which the energy bands are like this, so this is the minima and your maxima also happens to be, so this is the maxima, and if, so this band gap is called as direct band gap semiconductor when K minima is same as K maxima. Okay, there is no gap distance, there is no difference in these two K values. So, this is E, this is K. This is a direct band gap semiconductor. So, something like silicon is an indirect band gap semiconductor, and something like gallium arsenide is a direct band gap semiconductor. Now, this has profound implications in terms of optical properties. Generally, the light absorption is better in case of direct band gap semiconductor as compared to indirect band gap semiconductor, because light absorption, you have a photon and the photon causes a migration of electron to hole. So, since there is no change in the K value, the absorption of light is much better in case of direct band gap semiconductor as compared to something like silicon, where K value is different. So, electron has to change its K value. So, when you excite electron from valence to conduction band, it directly just does not go to valence band. It will have to change its K value corresponding to that energy level. So, you have some loss of energy here, and as a result the absorption is not very good. So, in general you can say that optical absorption is better for direct band gap semiconductor than in a okay. Now, there are a lot of details in this which I have not touched upon. So, unfortunately those are not, I mean it is not possible to go through them in this short lecture, series of short lectures. There are something you would need to know along the way, is something concepts of density of states, concept of Fermi energy and so on and so forth. So, essentially let me just talk about the Fermi energy a little bit. So, we can say what is we can begin with first density of states. So, when you have energy states in a given system, then we can define these energy states in the form of what we call as density of states. Density of states I can define as the number of energy states per unit energy in an interval dE. Okay. This is called as density of energy states, basically density of energy states. Okay. So, how dense the energy states are in a given interval, and this is, we can write this as dE as V over 2 pi square. So, there is a whole analysis behind this which I am not going to do here. 2m divided by h cross square to the power 3 by 2 into e to the power half. So, you can do this analysis of density of states in 1 dimension, 2 dimension, 3 dimension space. So, now density of states, when you plot it as a function of energy, then it goes as, you can see that it goes as e to the power half. Okay. So, dE goes as e to the power half. So, you can plot this as, so you can see that if you have E is equal to 0, the dE will be equal to 0 as well. So, this goes as something like this, right. So, this is dE and you will have E here. Now, when the temperature increases, then what happens is that when the temperature increases, the density of states tend to show a behavior around energy called as Fermi energy. So, this is, let us say, certain energy called as Fermi energy. Now, Fermi energy is generally defined by, so there is something called as Fermi energy is an energy below which all the energy states are filled at 0 Kelvin. Okay. So, you can say at 0 Kelvin Okay. So, basically Fermi energy is defined by this Fermi-Dirac statistics, which is probability of energy occupation. So, Fe is equal to 1 plus exponential of E minus Ef divided by kBT. So, when you plot this Fermi-Dirac statistics, when you plot Fe as a function of E, at 0 Kelvin the plot is something like this. This value is Ef. So, the probability of occupation is equal to 1 below Ef and at 0 above Ef. Now, when you plot, when you change the temperature, this curve changes its behavior in this fashion. So, it tends to go like this. So, this is at a temperature T1. If you go to temperature T2, goes like that, something like that, T2. So, it is not drawn very well, but something like that. Okay. So, basically what happens is that as you provide some thermal energy to the system, the electrons below Ef, they get enough energy. So, this is the band in which they get thermal energy, this is the band in which they move around. So, when you excite it, so of course, if you want to excite from energy levels which are far below E, you will have to provide a lot more thermal energy. For conduction, electron needs to be able to move into energy states above it, right, which means it must have some empty energy states around it. So, that is what the problem in the semiconductor. For conduction to occur, if you look at this EK diagram, electron has energy states available to move around, right. However, if you look at this situation where electron can move here, but if all these energy states are filled, where does it go? It has to go to energy states which are above. But if it does not have enough energy to jump to these energy states, which means it cannot move around. So, you need to provide that amount of energy. So, essentially that is what we are saying in Fermi-Dirac statistics, that there is a reference energy Ef below which all the energy levels are filled. So, this energy valence band may be up to this part only, it may not coincide. So, it is just a hypothetical picture. So, when you provide some thermal energy, the energy levels, the electrons which are residing just in the vicinity of Ef, they get enough energy so that they can go to energy levels which are available above Ef. And then there are lot many empty states around Ef in which electron can move around and conduct. As you keep increasing the temperature, more and more electrons jump in, but it happens, the whole thing happens in the vicinity of Ef. So, the number of electrons which have left here are the number of electrons which have reached here. Similarly, in this case, number of electrons which have left in this fashion have reached here. So, this curve is basically around asymptotic around half. Okay. So, number of electrons which have moved above Ef are the same as the number of electrons which have left below Ef. Okay. So, this we will continue in the next lecture. Okay.